Bismillahirrahmanirrahim. This video is from Mr. Sedra's book of 6th edition, question number 2.77 or 2.72 from the 7th edition. And this is on the request of a student from Turkey. So this is the question. The circuit shown in figure is intended to supply a voltage to floating load, those for which both terminals are ungrounded. So the load will be connected here and there is no connection of the load with the ground. While making greatest possible use of the available power supply. Now, no power supply is shown here, but actually I'm sure you recall that all operational amplifiers have these two power supplies connected, positive and negative generally, or it maybe have just one side and other side grounded. So this is the power supply, and we have to make greatest possible use of this power supply power. Now, one point, the operational amplifier has a very large gain, maybe thousands or 10,000 times. That does not mean that if we apply or if we supply 1 volt here, then the output will be 1,000 volt. No, the output is limited by the batteries. So it is maximum it can go to 15 or maybe slightly less in this case. Okay, now these are the three parts of the question that we have to look or solve. We'll tackle one at a time. The first part says, assuming ideal operation, sketch the voltage waveform at nodes B and C. So these are the nodes or the output B and C. So we have to sketch the output at B and C for a 1 volt peak to peak sine wave applied at A. So the input is at this point A, 1 volt peak to peak. That means half positive and half negative. That will make it 1 volt peak to peak. So, and then the second part of it is sketch V out. So let's first of all find VB and VC. And for ease, I have marked these as amplifier 1 and amplifier 2. Now, operational amplifier 1, it is a non-inverting amplifier. Now, if you look, the input is applied at the positive terminal. And when an input is applied at the positive terminal of an operational amplifier, this is a non-inverting amplifier. And the formula for non-inverting amplifier is given here, 1 plus RF over R1. Now this is RF and this is R1 and multiplied by the input VI. So in our case, it will be 20 divided by 10. And V in is VA. That means VB will be equal to 3 times VA. So we can plot it. This was VA, so we'll just multiply it by 3. So it will be 1.5 positive and minus 1.5 at the negative peak. Now operational amplifier 2. This is an inverting amplifier. You can see the input is going to the negative terminal. And for inverting amplifier, the formula is negative RF over R1 multiplied by V input. Now RF is 30 and R1 is 10. So putting in the value, VC output, this output will be negative 3 VA. The negative sign means it will be inverted. That means where there is a positive, the output will be negative. So 3 times this and negative. So when it is going positive, this is negative. When it is going negative, output is going positive. So this is the second output, VC. Okay. So now we have VB and VC. We have to sketch the output VO. Now the VO is actually VB minus VC. VB minus VC. That means we have to subtract this from this. So like 1.5 minus 1.5 will be plus 3 volts. So at this point, it will be plus 3 volt when this is going positive. and this is going negative, then it will be minus 1 volt minus 1.5, that means minus 3. So minus 3, and that is how you draw the VO output. Okay, and now we come to part B of the question. What is the voltage gain VO over VI or VA in our case? So we know this formula, and we have calculated the values of VB and VC as shown here, 3VA and negative 3VA. So we'll put it here. So 3VA minus 3VA, that means it will be 6VA. So V out is 6 times the input VA. And now the gain formula we know is V out over V in, V out over VA in our case. And this we move to the left hand side. So we will have VO over VA, which is equal to 6. So the gain is 6. Now we come to part C. Assuming that the op amps operate at plus minus 15 volt power supply and that their output saturates at 14 volt. So this is the transfer characteristics of the operational amplifier, and it says that it saturates at 14 volt. That means the output cannot go beyond this. So 14 volt is the hour limit. So 15 VCC is 15, but saturation limit is 14. Now, if we have a smaller signal, then the output will remain within the boundary. It will not exceed. But if you have a larger signal, like here, it will try to cross the 14 volt limit, but obviously it will get chopped off here. So this is our limit. Now, what is the largest sine wave output that can be accommodated? So we want to find out the largest sine wave which can be accommodated or which cannot get chopped off. Okay, so let's see here. We keep this in mind. Now this was VB. So if you are applying VB here, then the output should be within 14 volt, and we can always calculate what should be the V, because it was amplifying 3 times, so it will be 4 point something the amplitude of the signal. Anyway, so 14 volt positive, 14 volt negative is the limit for VC, VB, and same applies to VC, 14 volt, 14 volt. Now, so the largest sine wave output will be what? 14 and 14, if we add, it will be 28. Let's see from here. Output VB can be plus minus 14 or 28 volt peak to peak. So this is 28 volt peak to peak. Similarly, VC can be plus minus 14 or 28 volt peak to peak. So when we subtract this from this, then our from 14, and we have seen that 14 subtracted minus 14 will be plus 28. So one limit is plus 28 and the other limit is minus 28. So from here now we can write that peak to peak output will be plus 28 and minus 28 between this. So we can write it in this manner, that V out will be greater than equal to minus 28 volt and less than equal to plus 28 volt. And its peak to peak will be 2 times of this, that means 56 volt. The other part of the question says find the RMS value. Now the RMS formula we know is V RMS is 1 over 2 under root multiplied by V peak, not peak to peak. In our case, peak is 28. So 28 divided by under root 2 will be 19.8 volt RMS value. I hope you have been able to follow this. Please let me know through your comments. Thank you.